Hello, students. So this is the third video, which is section 6.2 on confidence intervals. We're going to do now confidence intervals for means. Last time, the first video we did was confidence intervals for proportions. All right, so let's share the screen. And let's see if I can right to. Give me a second here. Right to the textbook. Okay. All right, this is section 6.2. The very first thing that we talk about is the standard error for a mean. Right now, through section 5.2, we were using the standard error that we were reading off of a Statkey bootstrap sampling distribution chart. Upper right-hand corner, there was a standard error that we were using. But now we're sort of like not doing Statkey anymore. We're going to actually use formulas. So in general, the formula for the standard error for a mean is this formula right here. It is the standard deviation of the population divided by the square root of the sample size. Okay. Now, the central limit theorem, sample mean, states the following. If the sample size is large enough, then the sampling distribution of the sample means will be normal. Now, if the population is already normal, in other words, we look at the population and we see that it looks bell-shaped, then the sampling distribution will also be normal. And it doesn't matter what the sample size is. But if the population is skewed right or skewed left, then we need a sufficiently large enough sample size so that the sampling distribution is normal. Now, typically, we use 30, sample size of 30. That seems to be the rule of thumb that most textbooks use. In our textbook, it says 20 to 50. That's sort of unusual that this textbook would say that as opposed to other textbooks. But for our course and for the final exam, and as far as the math department is concerned, the sample size of 30 is the minimum sample size for us to assume normality for a sampling distribution of sample means. Okay. Now, if you remember, when we talked about confidence intervals for proportions, we use the special formulas, n times p and n times 1 minus p, and we had to make sure there were at least 10, both of those products to be at least 10 for us to assume normality for the sampling distribution of sample proportions. But if we're looking at means, if we're using our sample mean as an estimate for a population mean, then if the population is not normal, we need at least 30, n is 30, all right? There's no proportion that we're dealing with, so there's no n times p, because there's no p. So we just use n as at least 30, all right? And that you should put into your notes because it is not in the textbook, but almost every textbook assumes that. All right, so the sampling limit theorem says that the sample size is sufficiently large, and that means at least 30, all right? And the sampling distribution is normal. Now, one of the problems with this formula is that the numerator, the population standard deviation, is typically unknown. So what statisticians have recommended is that we replace the sigma with S, the actual sample standard deviation for that particular sample that you have. And so it's S divided by the square root of n would be an estimate of the standard error. However, if you do that, then what happens is the normal distribution can't be used anymore, all right? We have to use another distribution, which we call the t distribution. We'll get to that in a minute. But anyway, that is the standard error. So for example, they're saying here, in this example here, we have a sample of 500 Atlanta commute times. Now, commute times is going to be, it's a continuous random variable. So we're going to find its mean, 29.11 minutes. Out of those 500 Atlanta commuters, their average commute time is 29.11 minutes with a standard deviation of 20.7. In other words, if we entered all 500 commute times into our calculator or into Excel and found the mean and standard deviation, we would find these two numbers here. All right. So remember, S is the sample standard deviation. All right. So how do we find the standard error? Well, for part A, the standard deviation is 20.7, and the square root of the sample size is square root of 500, and that's equal to 0.93. So that's our standard error that we're going to use in determining our confidence interval. All right. Now, as I said a minute ago, if we use S instead of sigma, we can no longer use the normal distribution. We have to use a special distribution called the t-distribution. The t looks very much like a standard normal. All right, it has a mean of 0. Now, its standard deviation is bigger than 1. It's not equal to 1. All right, so it's a little bit different than the standard normal. But the t-distribution is useful when we use a standard error that's S divided by the square root of n. All right, so that's what's the most important. The t-distribution is going to be used instead of the z. All right, so the t-distribution is symmetric. It looks like the standard normal, but it's not quite the standard normal. Now, what's unusual about the t-distribution as opposed to the normal distribution, remember the normal distribution has two parameters, the mean and standard deviation. The mean and standard deviation will define any normal distribution. For a t-distribution, we don't use the mean and standard deviation. We use what's called the degrees of freedom. Now, I can go through a lengthy explanation of what that means, but it's unnecessary. You just have to know df for degrees of freedom is the parameter that we're going to be using. Now, how do we calculate degrees of freedom? It is very easy in this case. It is simply the sample size minus 1. So, for example, the case that we just looked at, let me just move this picture here out of the way. Case we were just looking at, where the sample size is 500, the degrees of freedom would be 499. All right, so that's all you have to know about it. It is the one number that you need to put into your calculator, and we'll do examples of that. One number that you need to put in your calculator to help us find a t. All right, so we'll do that in a few minutes. All right, so that's the key point. The t-distribution is going to be used whenever we use this formula here, S divided by the square root of n, for our standard error. Now, if you happen to know sigma, if there's a good estimate for sigma, then we can use sigma divided by the square root of n. In other words, the population standard deviation divided by the square root of n for standard error. And then we can use our standard normal to find the z. Okay. And this is just some rough estimate to show people that the bigger the sample size, which means the bigger the degrees of freedom, the closer a t-distribution looks like a standard normal. All right, so you could read through this. It's important to understand that if the sample size is less than 30, then for us to work to create a confidence interval, the way that we're learning how to do it, it requires that the population is normal. All right, bell-shaped. Let's put it that way. It's bell-shaped. If the distribution is not bell-shaped for the population, if it's skewed left or right, then we have to make sure that the sample size is at least 30 to basically construct our confidence interval. All right. So, for example, here are dot plots of different samples of different sizes here. Here's a sample size 50. Now, 50 is bigger than 30, so even though the particular sample itself is skewed, they're using the sample to replace the population since we don't know much about the population. Notice it's skewed right here for that one sample. But since n is bigger than 30, it's 50 in this case, we can use the normal distribution for our sampling distribution of sample means. In the middle here, notice sample size is 8, that's less than 30, so the sample should look symmetric, and it does. So we can use it in this case, it's okay to use the t-distribution. In this case, however, it's skewed to the right, and the sample size is less than 30. In case C here, we cannot use the t-distribution we can't construct our confidence interval in the normal way. All right. So one of the requirements, and remember, we're going to, whenever assumptions are going to be asked for in the final exam, one of the assumptions is that this sample is randomly selected. And in this particular case, we have to check to see, number one, is the population normal? The problem will tell you if it is or not. If it's not normal, then we have to check the sample size. Is it at least 30? And those are the assumptions that we have to make. Okay. And notice here, degrees of freedom, df, is the one parameter that we need to use when we use our t-distribution. And notice it's just simply the sample size minus 1. Right? So very easy to remember. All right. All right. Now, how do you use the t-distribution? For example, what if I gave you a curve, and let's say we wanted to find the middle. Let's see what we have here. The middle 95%. Okay, the middle 95%. We want to find the endpoints. Now, if this is a t-distribution, not a standard normal, it's very important. You have to distinguish between the two. If you're going to be using the t instead of a standard normal, then to find those endpoints, you have to use what's called inverse t. So for example here, degrees of freedom is 15. That means the sample size was originally 16, all right, in this case here. All right, and we're assuming that the data is bell-shaped. The sample size 16 is less than 30. All right. So let's go to inverse t with our calculator. And I'll show you how it works. Very easy. Just give me a second here. Share my screen again. Now, for those of you who have the 83 calculator, unfortunately, you don't have class the week of November 8th and 10th. Those were the days I was going to update your calculator. So I'll show you towards the end of our meeting. I'll show you what you need to do. In essence, I'm not going to teach you how to do it. You'll have to do it yourself. There's YouTube videos to show you how to program your 83 calculator to add inverse t to it, because 83 calculators did not have inverse t. All right, so let's go hit second, go back to our distributions. And again, for those with the 84 calculators, you'll have inverse t. You hit enter. It's going to ask for the area to the left. This is no different than inverse normal. Okay. So let's say we wanted to find that right endpoint. We have 95% in the middle. We wanted to find the right endpoint. We know that the area to the right is 0.025, right? 2.5%, which is half of 5%. We have 95% in the middle, 2.5% in each tail, add up to 5%. So we have 1 minus 0.025, or 0.975 is our area to the left. Now, if the sample size is 16, our degrees of freedom is 15. That's what you type in here. Notice there's no information you have to put in about mean or standard deviation. Scroll down, hit enter. All right, and hit enter again. And there is your right endpoint. Okay. Now, your left endpoint will just be the negative of that. Okay. 2.131. Now, make sure that if you have to use the t, you use inverse t to find the endpoints. Don't use inverse normal. That's for normal distribution. for standard normal or any other normal. For the t-distribution, we use inverse t, and that's the number that we use here. Back to the textbook. We have 2.131 approximately. There it is, 2.131. There it is. And of course, I said that the left one would just be the negative. It's like a standard normal. It's symmetric. Okay. All right. So that's how you do it. You use degrees of freedom, but it's done exactly the same way as an inverse normal, except you use degrees of freedom instead of a mean of 0, standard deviation of 1. It's pretty easy to use. Now, again, those of you with 83 calculators, if you just be patient, I'll show you what you need to do. And I'll give you an example of a YouTube video that you can watch so that you can do the steps yourself while you and program your calculator to do this. All right, to create the inverse t function in your calculator. All right. Now, that was all that you needed to know for that distribution section in 6.2. We do have, of course, our confidence interval section itself. Now, remember, to create a confidence interval, for a mean in this case here, the estimated population mean, we have our sample mean as our sample statistic, and we add and subtract the margin of error. Remember, that's the general formula for a confidence interval, margin of error. Okay, margin of error consists of two things. All right, if we are dealing with a, whether it's a proportion or a mean, it's two things. There is what's called a critical value. That's the endpoint of the right endpoint of the confidence interval. Whatever that endpoint is, we're going to find it either using inverse normal or inverse t, depending on the circumstance. And then multiply that by the standard error. So the margin of error is the multiplication of two things, the critical value and the standard error. Now they chose z here because z was used for what? It was used in section 6.1, right? When we wanted to find the margin of error for to estimate a population proportion, right? Proportion. And remember the standard error for that was the square root of p times 1 minus p divided by n, right? So we had defined the z for that particular level of confidence, middle area, right? And that was the right endpoint. And then the standard error was just that square root formula. Now for means, if we determine that we have a good estimate for the population standard deviation, then we could use for the standard error the sigma divided by the square root of n. And then we just multiply that by z, the standard normal right endpoint for confidence level. However, as I said a little while ago, sigma is typically unknown. So we have to use s instead. And therefore, what we have to do is we have to not use z anymore. If we use s in our standard error formula to replace sigma, in other words, we use this formula here, we have to replace the z with a t. We have to find the right endpoint for the t, just like we did a few minutes ago when we found inverse t. We have to do that. All right, so I'm just going to scroll down here. And by the way, in the final exam, the math department assumes that for the most part, sigma is unknown. So in this section, we're strictly going to look at cases where we need to use s, the sample standard deviation, instead of sigma, the population standard deviation, in the standard error formula. So if the sample statistic is the sample mean, x bar, and the standard error is going to be s divided by the square root of n, then the confidence interval will be the sample statistic x bar plus or minus t star times s divided by the square root of n, where t star is the endpoint for the confidence level. The T endpoint. And we're going to use inverse T to find that, just like we did a few minutes ago. All right, so just a little bit of change, not a big deal. Let's do an example here. So it says here, United Airlines Flight 433 is a nonstop flight from Boston's Logan Airport to San Francisco International. During 2019, it was scheduled to leave each day around 6 a.m. and arrive around 10 a.m. Pacific time. Due to the 3-hour difference between the time zones, the flight's expected to take about 7 hours, 420 minutes, including time spent taxiing on runways and waiting to take off. An important factor in scheduling flights is the actual airborne flying time from takeoff to touchdown. All right. The data in flight 433 contain the airborne time in minutes for flights on 28 days in 2019. All right, so we have N is 28 in this case, just a little bit less than 30. And if we plot it, notice it's somewhat symmetric, a little bit symmetric, I would say. So even though it's below 30, we can use the T distribution in instructor confidence interval. Now, what is the degrees of freedom? Well, since there are 28 of these dots, 28 different flights, right? We're looking at the number of flights here with the minutes airborne. Then the degrees of freedom is 28 minus 1, which is 27. There's 28 of these samples. The sample size is 28. So the degrees of freedom is 27. All right. Remember, it's N minus 1. It's not N, the sample size. It's the sample size minus 1. Now it says for a 95% confidence interval, let's calculate it, okay? Well, X bar, the mean, is 371.1. That's what, if you had put this into your calculator, right? You happen to put this data into your calculator all 28 times and went to one variable statistics and looked things up, you would see that the sample mean is 371.1 and that the standard deviation S, remember that's the sample standard deviation, is 16.7. You see the two numbers here. Here's your mean, 371.1 minutes. That's your average sample time for the 28 flights, and the standard deviation of those 28 numbers is 16.7 minutes. Okay, so notice that the standard error is simply going to be 16.7, that's the S, divided by the square root of 28, which is the square root of sample size. Now remember, this is very important, it's asking for the sample size here. In the standard error formula, it's not asking for degrees of freedom. Don't get these things mixed up. It says N here, that's the sample size, you put 28 there. You're going to put 371.1 for your sample mean, all right, for those 28 times. So what's the other component of this? It's the T. The T times the standard error is going to give you the margin of error. This whole thing here. How do you find the T? Remember, degrees of freedom is 27. All right, degrees of freedom is 27. So let's now go to our calculator. Now remember, it's a 95%. So again, the area to the left is going to be 0.975. The middle is 95%. We'll scroll down. Now, remember the sample size is 28. Degrees of freedom is 27. So we type that in, hit enter. 2.0518. We're going to round to 4 decimal places. 2.0518. Back to the book. And they rounded to 3 decimal places, 2.052. So they multiply 2.052 times this ratio, which is the standard error. They came out to 6.5. 6.5 is the margin of error. On a multiple choice test, if I ask for the margin of error, you're going to put 6.5. If I ask the standard error, it's going to be 16.7 divided by the square root of 28, whatever that number is. That's the standard error. What's the critical value? 2.052. Critical value is that right endpoint of the confidence interval. That's right. It is the right endpoint. It's the right endpoint, either a standard normal Z or a T. Now, by the way, the T is only used for means, never used for proportions. For proportions, the standard error is the square root of P hat times 1 minus P hat divided by N, right? The square root of all of that. There's nothing in there about a standard deviation. So for proportions, we can use the Z. All right, but for when we deal with when we have a confidence interval estimating means, population means, then we have a choice. We can use a Z or a T, depending on whether the sigma, the population standard deviation, is known. If it's unknown, we use a T. If it's known, we use a Z. Simple as that. All right. All right. And that's it. That's how easy this is. All right. And then we do our interpretation exactly the same way. We say we're 95% sure that the true population minutes for this flight, that means for all possible times, past and future, past, present, and future, all times that this flight is going from Boston to San Francisco, that the actual mean, the overall mean, is, we're 95% sure it's somewhere in between those two times. And remember, this is very important, it's not always between these two times, all right? Just because of the sample that we're using that had us for the 28 flights. If somebody else picked randomly 28 other flights, they would get a different sample mean and a different confidence interval, different 95% confidence interval. Even if they picked 28 flights, they would most likely pick 28 different flights, not the 28 that were selected here, okay? And as a result, they would get a different confidence interval, but they could say, for that particular confidence interval, we're 90% sure that it does contain a true population mean, all right? It's not a probability, remember that. It's just, we're hoping that out of all the 95% of all possible samples that do contain the true population mean, we're hoping that this particular one is one of those 95%. All right, that's what we're hoping for, and that's what we mean by 95% sure. All right, that is the proper interpretation. Okay, and they give other examples here, but I think what we'll do now is, and let's actually do one more thing, and then let's do a couple more examples, and then that'll be it for the video. And of course, I do have to talk a little bit about the people with the 83 calculator. So we have to talk about that. Now, researchers, and I had talked about this before. I think we did this in the last video for section 6.1. Many times, or almost always, a researcher needs to know before they collect any data what the minimum sample size they need for a certain level of confidence, okay? And they may want to have a certain width of the interval. You know, they don't want an interval too wide. What do? They take the margin of error formula, which again is T times S divided by the square root of N. T times S divided by the square root of N. Now, as you might have guessed, as you probably guessed, if we rearrange this formula and solve for N, we would get this formula here. In other words, we would square both sides, do a little bit of algebra, and we would get that N is equal to this. Although notice this formula is different than the minimum sample size formula that we used in section 6.1 when we did the confidence intervals. Now here's the problem. This is all done before we actually get the sample. So we don't have an S. We don't have a sample mean or standard deviation because we don't have a sample. So we can't use S. We have to use sigma, unfortunately. So we have to have an estimate for sigma. All right, some estimate. Even if it's a rough estimate, we have to have some estimate. And we can't use t, because remember, t depends on the degrees of freedom, which is calculated from n. So if we don't know what n is, how can we calculate t? So we actually have to use z instead of t, and we have to use sigma instead of s in this formula down here to find the minimum sample size. So here's the deal. The deal is that you have to come up with an estimate for sigma. The problem will give it to you, so don't worry about it. It's not like you have to figure it out yourself. The problem will give you some way of figuring it out. And we're going to use z, the standard normal, all right, because t, we can't use it all when we're trying to figure out what n is. All right, so down here it says it here. We could use a previous study, maybe, to figure out what the standard deviation is, some estimate for it. Another little formula that they sometimes use, and you should be familiar with this, is sometimes if we have data, we take the range of the data. That means the minimum minus the maximum minus the minimum. That's, we all know what range is, and divide it by 4. So if let's say over a long period of time, many days, many calculations are done for the sample mean, or not for the sample mean, for the continuous variable that we're measuring, and we sort of know what the smallest number is out of all those numbers. We sort of know what the largest number is. We take the difference between those two. In other words, we calculate the range and divide it by 4. That's assumed to be a decent estimate of the standard deviation. All right. So that is an estimate for sigma. All right. So we have to estimate sigma. We use z instead of t. In other words, we use this formula here. Now, the problem itself will tell you the margin of error. Usually the key word that's being used is within. They say within 2 units, within 3 units, whatever that is the margin of error. All right. So what you do is you calculate your standard normal right endpoint for the confidence interval. You multiply it by the estimated standard deviation, and you divide it by the margin of error that the researcher would like. You square that ratio, and then you round up to the next whole number, and that gives you the minimum sample size. So here's an example. I guess we're going back to this problem with the flights from Boston to San Francisco. Suppose we want to calculate our minimum sample size, and we have a certain requirement. All right. So number one, the requirement is we want to calculate a 95% confidence interval. We already should know what that z is for 95%. We know it's 1.96. Okay. And we also want, let's see, here we go. We want the interval to be, we want the estimate to be within 2 minutes of the actual mean. In other words, we want, here's the word within, 2 minutes. So 2 is the margin of error. That's what they're saying. They want the maximum, if possible, the maximum difference between the population mean and the sample mean to be 2 minutes. All right, so be within 2 minutes. So we want a margin of error to be 2. All right, so let's look at our formula here. Now they did say here that let's use, let me see what they said here. Let's say they're estimating that the population standard deviation is 16.7. That's what they're doing. They're saying, let's estimate it from maybe some previous studies. And we're going to use that for our estimated population standard deviation. So we're going to plug that in to here for sigma. 1.96 is the z. Again, inverse normal. You go in inverse normal, and you put 0.975 in for the area to the left, 0 for the mean, 1 for the standard deviation, 1.96. All right, it's 1.96, and our margin of error is 2, because they're saying they want the accuracy of the estimate to be within 2 minutes the actual population mean. So that within word here, see the key word here, within, tells us the margin of error. And if we do all this and square it, we get 267.8. And then you have to remember the square here. And you round up to the next whole number, 268 flights. Now remember, in the original study, there were only 28 flights. Okay. And notice the margin of error was 6.2. All right. I mean, excuse me, sorry, that's 6.5, right? If we go back and we look at the previous problem and we calculated our margin of error, remember it was 6.5. That was with 28, sample size is 28. Now, if we want to, we want a margin of error of 2, obviously we have to increase our sample size, and we have to increase it dramatically. Instead of having 28 people, we need 28 flights, we need 268 flights in our sample. All right, so that's called a minimum sample size problem. All right, and that's it for this section. Again, let's just do a couple more things here. Let me just go back to the beginning of the section here. All right, so let's just look at the very first problems in back of this section, very first exercises. And notice here, we're being asked to use the t-distribution to find a confidence interval for a population mean mu. Right? So it says, given the sample results, find what are we being asked to find? We're being asked to find the confidence interval. All right. So let's actually do 6.89. Something you can do on your own. Notice that the confidence level is 95%. Right. And by the way, when you write down confidence level, typically people write C equals 0.95. C stands for confidence level, all right, so that you know that. So how do we find the confidence interval? Well, the mean X bar is 12.7. The standard deviation, the sample standard deviation is 5.6. Sample size is 30. Notice the sample size is sufficiently large, right? So we know that according to the central limit theorem, the sampling distribution is going to be normal. We don't even have to worry whether. Now it does say here, if you look in the body of this problem, it says assume the results come from a random sample from a population is approximately normally distributed. All right. Since they tell you the population normally distributed, it doesn't matter the sample size. We can have a sample size of less than 30. The sampling distribution will be normal. And remember, those are the two assumptions, right? To construct confidence interval. The sample size is the sample was randomly selected, and number two, one of two conditions are met. That is, either the population is normal, which means the sampling distribution is normal, or the sample size is at least 30, which means the sampling distribution is normal, even if the population is not. All right, so here we have our numbers here. Sample mean of 12.7, sample standard deviation of 5.6, sample size of 30. So let's go to our calculator, and I'll show you a very quick way of calculating our confidence interval for this. Let's go to our calculator. Share the screen again. Calculator. Clear this out. Now, the problem does not give us a population standard deviation. It gives us our sample standard deviation. So we have to use a t distribution. And so let's do that first. Let's calculate our t. We're going to do second variable distribution, and we'll go down to inverse t. Now this is 95%, so 0.975 will work. That's the area to the left for a 95% confidence interval. Degrees of freedom, well, sample size is 30. So the degrees of freedom is 29, 1 minus 30. We'll scroll down, hit enter. hit enter again. There's our, it's our t. All right. Now we multiply that by the standard error. So I'm just going to hit the multiplication. I'm just going to do this all in one step. And I'm going to multiply that by S, the standard deviation, sample standard deviation, which is 5.6. And then we're going to divide by the square root of the sample size. The square root of sample size. The square root of 30. Remember, use sample size here, not degrees of freedom. All right. So the 2.045 is our critical value. That is our t, the right endpoint of the confidence interval for t distribution. We multiply this by the standard error, which is s divided by the square root of n. In this case, 5.6 divided by the square root of 30. So if I hit enter, what do I have here? This is the margin of error. That's the margin of error, 2.091. Now, how do I come up with our confidence interval? Well, if you have an 83 calculator, I think there's some difficulty to scroll up and highlight that previous answer. So one way of doing this is to store this margin of error. I'm going to hit the store button. And I'm going to put this in A. Remember, it's alpha A. Hit enter, and that 2.091 is now in alpha A. So the mean, remember, is the sample mean is 12.7. The lower endpoint of the confidence interval is going to be minus the margin of error. No, I put the margin of error in alpha A. Hit enter. There's the lower end of the confidence interval, 95% confidence interval. Then I do 12.7, and I'm going to add A, alpha A, hit enter, and there is my upper end of the confidence interval. So if I round the confidence interval to 3 decimal places, then the lower end is going to be 10.609, and the upper end of the interval is going to be 14.791. Let's now go back to the textbook. All right, and if we just look at the solution for it, we should see 10 point, well, actually they're rounding at the 1 decimal point, which I would not do, but there's your same thing. But you don't need to round anything until the very last step. So if I ask you to round the endpoints to 3 decimal places, then that would be the very last step. And you can do exactly what I did in the calculator. There's no need to round as you go along. All right, no need to do that. And you'll end up with the right answer. There's your confidence interval. And you can say something like with 95%, I'm 95% sure that using this particular sample, the true population mean is somewhere in between 10.609 and 14.791. Okay. Easy enough? All right. Let's do a 90% confidence interval problem. Let's try 96.91. So let's do in this case, it's 90% is our level of confidence. Okay. And then for this one, the sample mean is 3.1. The sample standard deviation is 0.4, and n is equal to 100. Okay. This is 6.91 we're going to do now. Sample mean is 3.1. The sample standard deviation is 0.4, and the sample size is 100. All right, so let's go to the calculator and calculate this confidence interval. And again, we'll do it exactly the way I did it a minute ago. I'll calculate my t again. Now I have to do a t once again because I am not given the population standard deviation. I'm given the sample standard deviation. All right, I'm going to calculate the t. Okay, now, this is a 90% confidence interval. So that means 10% is remaining, 5% on each tail, right? Half is on the left tail, half is right tail. Therefore, the Area to the left of the right endpoint must be 95%. This is for a 90% confidence interval. Now, n is 100. It's your sample size. That means 99 is our degrees of freedom. And 1.66 is going to be our t, critical value. I'm going to multiply that. You can see how quickly this goes. Multiply that by S, which is 0.4. Be careful. Make sure you use S, the standard deviation, sample standard deviation. And I'm going to divide this by 100, square root of 100, right? The square root of 100. That's 10, by the way, but I'm just going to type it in anyway as a square root. So make sure you don't divide by 100, you divide by the square root of 100. Hit enter, and there's my margin of error, 0.066. I'm going to store it in A, alpha A, and then I'm going to type in my sample mean of 3.1. I'm going to subtract my margin of error, alpha A, enter. There's my lower endpoint of the interval, and then I'm going to say 3.1 plus the margin of error, alpha A, that's where I put my margin of error. There's my upper endpoint. I'm done. There's my 90% confidence interval. So I could say something like I'm 90% sure that for this particular sample, the true population mean is somewhere in between 3.034 and 3.166. I was rounding to 3 decimal places. All right, that's it. That's it. That's all there is to it. Pretty easy, I hope. I hope you find this easy. Confidence intervals should be much easier than hypothesis tests to do. And I hope you're all following along and doing this with your calculator. All right, that's important. And you do math, and particularly statistics, that you follow along with a notepad, a pen, and your calculator right next to you, and you follow and do it. You can always, this video is recorded, so you could stop it and go back, do things like that. All right, let's actually find a nice word problem here. Done everything but a word problem. And by the way, actually, let's do one more. Let's do the 99% confidence interval. Let's do 6.93 here. So let's do a 90% one. Let's give me 99% one. So 6.93. Notice that the mean is 46.1. Sample standard deviation is 12.5. Sample size is 10. Now notice 10 is below 30, but we were told that the population is normal. So we can assume that the sampling distribution is normal, even if the sample size is less than 30. All right, so we can still do this whole construction process for the confidence interval. And let's go back to our calculator and do this one. This is a 99% one. And I guess it would be good to see how this is done. So let's do it. Again, it's very easy and quick to do one of these. We always start with the t. In this case, again, we have to have a t instead of a z. The standard deviation is unknown. Population standard deviation is unknown. So we go to inverse t, hit enter. And the area. Now, what are we going to use to the area to the left? Well, if it's 99% in the middle, that means 1% is left. Half of 1% on the left and half of 1% on the right. Half of 1% is 0.005, and therefore the area to the left is going to be 0.995. Right? What's the degrees of freedom? Well, n is 10 in this case. Sample size is 10, so the degrees of freedom is going to be 9. Enter. Notice how big the t critical value is, 3.2498. Again, I'm going to multiply that by the standard error, which is going to be S, which is 12.5, sample standard deviation, right? Divided by the square root of the sample size, square root of 10. We use 10, not 9, use 10 here, sample size. And the 12.846, that is our margin of error. So once again, I'm going to store it in alpha A. And then I'm going to take my sample mean, 461, I believe. Actually, let's go back. I just want to verify. For some reason, I think I wrote this down wrong. Let's just verify the numbers again. All right. 46. Yeah, I did this wrong here. It's 46.1, right? 46.1 is the sample mean in this case here. Well, you don't know what I wrote, but I did write it down wrong. So let's go back and share the screen with the calculator. All right. So we have our margin of error 12.846, and we're going to take our 46.1. Okay. 46.1 minus our margin of error, which is an alpha A. Here's our lower end of the confidence interval, 33.254. We're on the 3 decimal places. And then I do 46.1 and add the level of, add the margin of error, and I get my upper end, 58.946. So 33.254, lower end, 58.946 on the upper end. Notice how wide the interval is. That's because we wanted a 99% confidence interval. And if you remember, the larger the level of confidence, the wider the interval. So that's why the interval is so wide. Okay, that was one of the things I showed you in class. Okay, so let's go back to the book. And this just double check to make sure the solution is right. There it is, 33.25. The rounding is 2 decimal places, 58.95. That's exactly what we did through the calculator. All right, so there you go. Easy, 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 easy. Most of you should have no problem. All right. Now, here are cases here where they're being, in Skill Builder 2 here, they're asking you to find the minimum sample size. If they give you the margin of error, all right, and they give you the level of confidence, and they give you, assuming a previous sample S is equal to 18. All right, now, remember the margin of error is going to be, all right, T times S divided by the square root of N. If we squared both sides, we end up with T times S divided by the margin of error, the quantity squared, right? It's T times S. Now, if we look at 6.95, for example, here, it says the margin of error is 5. All right, so that's our margin of error is 5. And they're saying I want a 95% level of confidence, and assuming a previous sample had S is equal to 18. Now, why do they give you that? Because they're making the assumption here that we should use S, the previous S, as a estimate for the population standard deviation. All right, it's from a previous study, and we'll use that as our estimate for sigma. All right, so let me go to our calculator and do this. It's a little more complicated doing this. It's not a big deal. So we're going to use parentheses here because we're going to be squaring two things. And actually, the numerator is going to be, if you remember the formula, it's going to be the one that we really need to use is Z times sigma. Z times sigma is the numerator, and the denominator is margin of error, and that whole thing is going to be squared. So I'm going to open up a set of parentheses. Okay. And so I said Z. Now this is a 95% confidence interval. So remember the Z is 1.96. Know that for a fact now, right? I don't have to do an inverse normal. Remember, you have to use inverse normal when you do minimum sample size. I'm going to multiply this by our estimated population standard deviation, which you're getting from a previous sample that was done. So we're going to use 18 in this case here. And then we're going to divide by the margin of error, which is 5. And then we're going to square this whole thing. Now, once I use parentheses, if I hit the x squared button here, this whole thing here gets squared. The whole parentheses gets squared. This is how you should do it. So you just do, in this case, the Z, 0.96, because I want a 95% confidence interval. I'm going to have my estimated sigma, population standard deviation. We're going to use 18 from a previous study. And I'm going to divide by the margin of error 5, and I'm going to square this whole thing. But hit enter, I get 49.78. And I'm going to round up. I don't care what the decimal is there. Round up to the next whole number. I need 50 as a minimum sample size. Right, that's my minimum sample size for this study. So the requirements were 95% level of confidence, and I wanted my margin of error to be 5. Right? Margin of error is 5. So now I'm going to, oops, you know what? I forgot. I apologize. I forgot to share the screen. So let's do it again. So I'm going to clear this out. I was talking without you seeing any of that. There's always at least once during these videos I do that, so I apologize. It's just very easy to do. So again, I'm going to open up a set of parentheses, and the numerator is going to be, for the minimum sample size problem, it's going to be Z times sigma Z, which is the critical value, the standard normal critical value. It's 1.96 in this case here because it's 95% confidence interval. And 1.96 is the right endpoint for that. 18 is our estimated population standard deviation. We got that from a previous study. Multiply that by 18. And then I'm going to divide by the margin of error that I would like, which is 5. Close parentheses, and then hit the x squared button, which will square that whole thing, which is what I want. Hit enter. Here's my 49.787, and then just round up to the next whole number. My minimum sample size that's required here is 50. So let's just double check, make sure that I did this problem correctly. All right, and it was this one here, 6.95. Let's see if the answer is 50. Oops. There it is. And notice they say n is greater than or equal to 50. That means it's the minimum sample size is 50. You can certainly have more than 50 if you want, but if you want to meet those conditions, that is, if you want 95% level of confidence, you want your margin of error to be 5, you need at least 50 people in your study, or things in your study, whatever the sample is about. All right. Now, one thing I want to clarify to you, if you have a margin of error of 5, that means the length of the whole interval is 10. Remember that? Because the formula for creating a confidence interval is you take your sample mean and you add and subtract the margin of error. So when you subtract the margin of error and then you add the margin of error, you're going to have 2 times the margin of error as the length of your confidence interval. Okay. All right. So let's stop sharing here. Back to the book. Let's just do a word problem. See if we can find a nice word problem. Okay. I guess this one here is good enough. Forest fires in Portugal. All right. So it says here, a study of forest fires in Portugal looked at the effect of many variables on the area of forest that is burned by the fire. The study included 517 forest fires. So that's your sample size, 517, and found a mean area burned of 12.85 hectacres, right? So that's 12.85 is your mean. And it says the standard deviation is 63.66. All right. And notice in this case here that the mean is much smaller than the standard deviation. Sometimes you'll see examples like that. All right. And it says, notice here, the standard deviation is much bigger than the mean because the data is very right skewed. Now, because the sample size is 517, even though the population is right skewed, we can assume the sampling distribution is normal because the sample size is much larger than 30. All right. So it says find and interpret a 90% confidence interval for the mean area burned by all forest fires in Portugal. So that's the population, all forest fires in Portugal, and we're looking at 517 of them that were randomly selected. Okay, we have all the data that we need. Let's go to our calculator and figure out the confidence interval here. Okay, so clear our screen. Again, we'll calculate our T. Now remember, there's nothing about a population standard deviation here, so we must use a T as our right endpoint, our critical value for the calculation of our margin of error. Okay, so we'll go to second inverse T. Scroll down to inverse T. All right, 90% confidence interval means the middle area is 95% of our T. That means the two tails are 5% each. That means the area to the left of the right endpoint is 0.95. Degrees of freedom, well, and the sample size is 517, so we're going to use 516 as our degrees of freedom. Hit enter. There is 1.6478. That is our 90%. That's our T critical value. We're going to multiply that by standard error, and our standard error is going to be S, which is 63.66. Divided by the square root of the sample size, square root of the sample size, which is 517. Okay. Hit enter, and that 4.613 is our margin of error. Our margin of error. So what are we going to do now? Well, we'll store that margin of error again in alpha A. Now we simply take our sample mean, 12.85, and we'll subtract the margin of error, alpha A. Here's our lower end of the interval. And then we're going to take 12.85 and add the margin of error, alpha A. Okay. There's our upper end. For a 90% confidence interval, if we rounded to 3 decimal places, would be 8.237 up to 17.463. And we can state that we are 90% sure that for this particular sample of 517 forest fires, the true population mean is somewhere in between 8.237 and 17.463. Okay. That's how we do it. And don't be fooled by the word problem. The word problem is giving us the same data as the others that we were doing. Okay, and if we show the answer, should be, there it is. Now it's a slightly different than what I'm showing you, but probably because of rounding. Now we didn't do any rounding until the very end, and probably the people who solved the problem here did rounding earlier when they were doing all these calculations. So they did some more rounding, but the way I did it is the best way of doing it with your calculator. All right, and that is it for that type of problem. And then let me just see if there's anything else here that we can look well. Looking at, see if we can find something. A lot of different ones here that you could probably do if you want to. By the way, if they give you data and you enter it into your calculator, you just simply read off from one variable statistics your sample mean and sample standard deviation. So it's not a big deal. If the mean and standard deviation are not given, but the data set's given, you enter the data sets as a list, and then go to one variable statistics and look up the mean and sample standard deviation. So not a big deal. All right, so that is it. I showed you how to do minimum sample size also. And the final thing I wanted to do, let's stop sharing here. I want to just find this particular thing. Here we go. I want to share with you, this is for people who have the 83 calculators, okay? Those of you with the 83 calculators, just give me a second here. Okay. So I just pulled out one YouTube video that I found. There are a few of these. There's one right here. This is saying loading INVT, inverse T, on a TI-83 calculator. This is an actual video. And it lasts, let's see, it looks like 12 minutes and 34 seconds. So it's not going to take a whole lot of time. And of course, you can always pause it while you're watching it. And what's going to end up happening is you're going to program this into your calculator. In other words, there's a program button in your 83 calculator, so people with 84 calculators have it. And what's going to happen is you're going to program it by following the steps here. And it's going to end up being called INVT. And then when you want to use it, what's going to happen is you'll hit your program button, you'll scroll down to the INVT, hit enter, and I believe you have to enter a second time. And then it's going to ask for the area to the left. You'll type it in. And then it's going to ask for degrees of freedom, or DF. You're going to type it in, and then hit enter, and it'll give you the right endpoint of the confidence interval. That's critical value. So follow the directions here. It's pretty easy. I think anybody can do this. Just type in as you go along into your 83 calculator. And again, it's this inverse T will end up being in the program. It'll be one of the programs that you'll be using. And again, they'll tell you in the video how to use it. Now, if for some reason this doesn't work or you don't feel comfortable doing it, you will need it for your homework, but the homework's not due till after I get back. So if worse comes to worse, when we meet again, I will program your calculator in class. But I would recommend that you try this on your own. It's not difficult. It's not scary or anything like that. You should be able to do it. All right, and there's a few of these out there. So just follow along, and you should be able to do this. All right, so this is what by the way, this is what I typed into Google here, loading INVT onto TI-83 calculator, and I ended up getting videos that look like this. So this is the very first one I saw. I played it. Person sounds very nice on there, very clear. So it should be easy for you to program your calculator. All right, so that's what I would recommend that you do while you're home. Do it as soon, do it after you listen to this video. All right, and then you'll be able to do the homework and practice everything I did in class. All right, all of those who have 83 calculators. You have an 84 calculator, you have inverse T as one of the distributions that are listed. This is just for the people with 83 calculators. All right, that is it. And that's about all I want to do today. So there's going to be one more video after this, which is going to be section 6.2 hypothesis test. And that one will come is the last of the 4 videos. So go ahead and try the homework in 6.2 for confidence intervals for means and see how it goes. And again, if you're having trouble, don't do all 3 attempts or all, I forget how many attempts you get. I think you get 3 attempts. Just do 2 attempts, stop, and wait till we get into class, because I will be doing lots of problem solving, which will prepare you for not only for the test number 3, but for the final exam. Okay, so that is it. And that'll be it for today. All right, so take it easy, and I'll see you soon.